Okay, so in this video we're going to look at the solutions to the Semester 2 T2 2016 paper for Phys 1121, that's Physics 1A. Okay, and I'll be talking you through them. I'm Dr. Elizabeth Engsman. So let's look at question 1. In this question we've got a toy car on a bench and it travels along the bench and then falls off, and we're told that the displacement of the toy car is equal to 0.20 plus 0.50 t squared, where x is in meters and the bench is 1.4 meters long and it is 1.3 meters high. So part A asks us to derive an expression for the instantaneous velocity. So in order to do this, we just need to take the derivative of the displacement. So the velocity in the x direction is just going to be dx dt. And when we take the derivative of 0.20, that just ends up being 0. And then when we take the derivative of 0.50 t squared, that ends up being 1.0 t. And that will be in the x direction, which is why we've put a subscript x down here, and that'll be meters per second. And then we're asked to calculate the instantaneous acceleration as the car travels along the bench, and this will be the derivative of the velocity, or the second derivative of the displacement. And taking the derivative of this function with time, we end up with 1.0 meters per second in the x direction. Now part B says at time equals 0 to find firstly the displacement. So we just need to find x at t equals 0. So we just substitute t equals 0 into this equation and we end up with 0.20 meters. So it starts 0.20 meters from the end. Part 2 then asks us for the velocity at t equals 0. So we can just substitute t equals 0 into this equation that we've derived up here, and that just gives us 0 meters per second, so it starts from rest. And then part 3, we're asked to find the acceleration at t equals 0. This has no t dependence, it's constant acceleration. So it's 1.0 meters per second in the x direction at t equals 0 as well. And then part C says, at what time does the car fall off the right-hand side of the bench? So we want to know at what time is x equal to 1.40, because the end of the bench is at 1.40. So we've got 1.40 is equal to 0.20 plus 0.50 t squared. And so we're trying to solve this to get t. So this tells us that 0.50 t squared is equal to 1.4 minus 0.2, so that's 1.20. So t squared is equal to 1.2 divided by a half, or 1.2 times 2, so 2.40. And so solving this, t is equal to 1.549 seconds, and so this is equal to 1.5 seconds to two significant figures. And we're giving it to two significant figures because the values up in this original equation up here are given to two significant figures, so we only know everything to two significant figures. And we don't need to consider what happens to the negative square root as the time is moving forwards in this case. We're not considering what happens at times prior to time equals 0. Okay, part D then says calculate the velocity of the car as it leaves the bench. Okay, so we know that it's got no vertical velocity, so we only need the velocity in the x direction to know the velocity. And so we can just use that the velocity is equal to 1.0 times t, and t is equal to 1.5 seconds. So 1.0 times 1.5, and so that is equal to 1.5 meters per second, and that's in the x direction. E then says how long does it take the car to hit the ground? Okay, so now we need to consider what's happening vertically, because vertically it's going to fall down, and when it's travelled 1.30 meters, that's when it's going to hit the ground. So we can say y naught is equal to 1.3 meters, and it's going to hit the ground when y is equal to 0 meters. So we're defining the ground as 0 and the bench height as 1.30. And so to calculate that time, we can use y is equal to y naught plus vy naught, the initial velocity in the y direction t, plus a half ay t squared. And what we're trying to get is this t squared. So in this case, we've got y is 0, y naught is 1.30. It doesn't have any velocity in the y direction initially, so this term here is 0. And then we've got minus, because the acceleration's downwards, a half times 9.8 times t squared, telling us that t squared is equal to 1.30 times 2 over 9.80. Okay, and solving this, we end up with t is equal to 0.515 seconds, but we should give this just to two significant figures, so that's 0.52 seconds. Now part F says how far from the right-hand edge of the bench does the car hit the ground. Horizontally, it travels with a constant velocity in the x direction. So the distance it travels x is just equal to the velocity in the x direction times t. And that velocity is constant once it leaves the bench, because the force is only being applied to it while it's on the bench. So the velocity it leaves with is the 1.5 meters per second, which we've calculated here. So then times 0.515, we should keep all our significant figures for the working. And then when we solve that, we end up with 0.77 meters, and that's given to two significant figures. Okay, now part G says find the velocity of the car just before it hits the ground, and remember to give both a magnitude and a direction. Okay, so horizontally it keeps going with a constant 1.5 meters per second, and vertically we want to know, well, how fast is it going at 0.515 seconds. So to calculate that, we can say Vy is equal to V naught y plus AT. And so this is equal to, initially it has no y velocity, so this is equal to 9.8 times t, and it's downwards because this acceleration is downwards. So 9.8 times 0.515. So this is equal to 5.047 down, and that's meters per second. So we can draw that here, 5.047, and what we're trying to get is this vector along here. Sorry, it's a bit hard drawing on this board, so that looks a bit wonky. And so to find out the magnitude of the velocity, we're going to have to use Pythagoras' theorem and take the square root of 1.5 squared plus 5.047 squared. And doing that, we end up with 5.26, which is 5.3 meters per second to two significant figures. But we also need to give the direction, so we need to find this angle here. So tan theta is equal to opposite over adjacent, so that's 5.047 over 1.5. And solving that on the calculator, we end up with 73 degrees. So we should say 73 degrees below horizontal. Okay, and then part H says calculate the change in total energy of the car from when it leaves the bench to just before it hits the ground. Okay, and we're meant to neglect air resistance and explain your answer in one clear sentence. Well, it's going to be 0. And the reason is initially it's going to have kinetic energy from the horizontal velocity and also potential energy from being above the ground. And then when it hits the ground, well, just before it hits the ground, all of that potential energy has been converted into kinetic energy. So initially it has both kinetic energy and potential energy. As it falls, the potential energy is converted to kinetic energy. So we have mgh is equal to a half mvy squared. So the potential energy is being converted into the vertical kinetic energy. The horizontal kinetic energy remains the same. But we've answered that question now. Question 2. Hopefully this made the Star Wars fans among you smile. Okay, so in this one we've got Han and Chewie trying to infiltrate an Imperial base. And initially we've got a situation where Han is hanging down like this and Chewie is on the slope here. And we're asked to draw a schematic Freebody diagram for Han and another for Chewie. So here's Chewie. And we need to label each of the vectors and pay careful attention to the vector representing the frictional force. So if I was doing this one, I'd do a kind of rough draft first and then draw it neatly afterwards. So let's put our rough vectors on here. So for Han, he's just got the two vectors acting on him. He's got the tension pulling him up, and then he's got his weight force pulling him down. Chewie, on the other hand, has the weight force pulling him down, the tension force pulling him up, and we've got the friction force, but we're not too sure at the moment which way the friction force is going to be acting. So for Han, we know that because he's at rest, the forces are balanced. So we know that the mass of Han times G is equal to the tension force. So this actually lets us calculate the tension force acting on him because we know these two things. So he's 75 kilograms and this is not Earth, so we've got a different value for G of 8.5. And solving that one on the calculator, we end up with 637.5 newtons as the tension force acting on Han. Now the same tension force is acting on Chewie. So now we'll consider Chewie. We're trying to work out the direction of this friction force by doing this. So we're going to consider the components acting on him parallel to the slope. So parallel to the slope, we've got the tension going upwards, and that is 637.5. And then this weight force, this has a component down the slope that way. So then we've got minus m, and in this case this is Chewie's mass, mg sine theta. And then we've got plus or minus the friction. And that equals 0. So let's work out what this is. So we can substitute in Chewie's mass is 120 times 8.5 times sine of 60, and solving that we end up with 883.3 newtons. So this is the weight force pulling him down. So since he's stationary, that tells us that the frictional force must be acting up the slope. Okay, so to draw our free body diagrams, here we've got Chewie. We've got the tension pulling that way, we've got the weight force pulling that way, and then we've also got the friction force pulling up that way. And for Han, we've got the weight force pulling down and then the same tension force pulling up. Okay, so we've done A, that's our free body diagrams here. Maybe just label that friction a bit clearer. And then part B says justify the direction of the frictional force vector in the diagram above. Okay, so this is our justification. So as Chewy is stationary and the tension is less than mg sine theta, the frictional must act in the same as t, i.e. up the slope. Okay, now C, calculate the magnitude of the static friction force between Chewy and the crater's slope. Okay, so we know that he's not accelerating, so Newton's second law tells us that the sum of all the forces has to equal 0. So we've got the frictional force plus the tension force minus mg sine theta. This is just taking all the components parallel to the slope is equal to 0, and we've worked out what t is. Up here it was 637.5 and mg sine theta was 883.3. So this tells us that the frictional force is equal to the 883.3 minus the 637.5. And solving that one, we end up with 245.8 newtons, except that everything's only to two significant figures. So this is 250 newtons up the slope. We don't need to say the direction because it just asks us for the magnitude. Okay, then part D, suddenly the rope breaks, Chewy and Han start moving. The coefficient of kinetic friction between Chewy and the ice-covered slope is 0.15. So mu k is equal to 0.15. Okay, so Chewy slides down the sloped outer wall of the structure, and we're asked for his speed once he's travelled 110 metres. Okay, so we've got a different situation now. There is no tension force. So in this case, we've got mg. So pulling him down the slope, we've got mg sine theta. And because that's the only force pulling him down, the friction force in this case is going to pull him up. It's going to oppose the motion. So we've got the friction force going up there. So we can use these forces to calculate his acceleration. Newton's second law tells us that the total force is equal to ma, and this is equal to mg sine theta minus the frictional force, and the frictional force here will be given by mu k because he's moving, so it's the kinetic friction, mg cos theta, and m here stands for Chewy's mass in all of these. So we can cancel these m's out, and then we can solve to find out what a is. So g, that's 8.5 sine, and we were told in the question that this was 60 degrees. So sine 60 minus 0.15 times 8.5 cos 60. And so solving this one, we end up with 6.7237 meters per second. Okay, but we weren't asked to get the acceleration, we were asked to get his final speed. So in order to do that, we can use the final speed squared is going to be equal to the initial speed squared plus 2 times the distance times the acceleration. And we've now got the acceleration, and we've got the distance, it's 110. And he starts from rest. When the rope breaks, he was at rest. So this is 0. So we've now got 2 times x, which was 110 times 6.7237. And so solving this one, we end up with, this gives us Vx is equal to 38.46 meters per second, which is equal to 38 meters per second to 2 sig figs down the slope. Okay, so we're on to part E. Now in this part we're told that there's a reflector shield that applies an average force of 1,200 newtons upwards on Han as he comes to rest. So we should work out the total force acting on Han. He's going to have the 1,200 newtons acting upwards, but then he's also going to have the weight force acting downwards. So the net force acting on him is 1,200 minus his mass, which is 75, times g on this planet, which is 8.5. So the net force acting on him is 562.5 newtons upwards. So this is the force which is working to bring him to rest. And so we can use impulse to work out how long it takes. We know that the impulse, force times time, is equal to the change in momentum, which is equal to mv. So this tells us that the time is equal to mv, well, the change in mv, this is the change in mv, over the net force. And his mass isn't changing, the velocity is. We know at the end that the velocity is 0, so we need to work out the velocity at the start. To work out the velocity at the start, we can use the fact that energy is conserved as he falls. So his initial gravitational potential energy is converted into kinetic energy when he hits the shield. So this will give us the velocity when he hits the shield if we take this as at the top of the cliff. So the masses cancel out and we end up with v squared is equal to 2gh, which is 2 times 8.5 times 99, because he falls 99 meters, which gives us his velocity before he hits the shield is 41.02 meters per second. And now we can substitute this back in over here. So the change in momentum, that's the final momentum minus the initial momentum. So the final momentum is 0 because he's come to rest, and the initial momentum, this velocity is downwards, and so this will be 75 times 41.02, and then we've got a positive sign because this is minus the initial momentum and this was downwards, so this is really, we can put a negative there to show that it's downwards, and this force is upwards as well, so that's positive 562.5, and solving that we end up with 5.47 seconds, which to two significant figures is 5.5 seconds, and that's to 2 sig fig. Okay, now Han and Chewie successfully escape from the ice base, and we're asked to derive an expression for the escape velocity of the planet, and we're told that the planet has mass mi, it's got some radius ri, and their shuttle has mass ms, and so we need to work out what's the escape velocity. To do this, what we can do is use energy conservation. To escape the planet, they need to have enough kinetic energy to overcome the gravitational potential energy of the planet and escape to an infinite distance. So they need enough Ke kinetic energy initially to overcome U, the gravitational potential energy. So initially they're at the radius of the planet here, and we know that U is equal to minus G, mass of the ice planet, mass of the shuttle, over the radius of the ice planet, and they need to get out to here, an infinite distance away, where U is equal to 0. So they need to have here, they need to have so by the time they get out here, it's fine if their kinetic energy is equal to 0, but they need to, this is their initial, this is final. Here we can work out what the initial kinetic energy is. So using energy conservation, we can see that out here the total energy is equal to 0. So in here, the total energy also needs to be 0. And so the kinetic energy must be equal in magnitude and opposite in sign to this initial potential energy. So we know that a half mv escape squared, and this is the mass of the shuttle here, has to be equal to g times the mass of the ice planet times the mass of the shuttle over the radius of the ice planet. And so the mass of the shuttle is cancelling out here, and we have that the escape velocity is equal to the square root of 2g times the mass of the ice planet over the radius of the ice planet. And so that's our expression for the escape velocity. Okay, so this one is question 3. And it's about Discworld, and we're told that Discworld is a thin disk 15,000 kilometers wide, and it rotates once every 72 hours. And then for the first part, we actually have to draw a diagram of Discworld and show the direction of north. So we're told, let's imagine that north is up the top here. So this arrow is pointing up the screen and it's pointing towards north. If we look at it from the north, then it's rotating clockwise. And so we can draw it as a disk like this. It's a narrow disk. And if we're looking from up here, then it's rotating clockwise. So it's rotating this way around, and the disk itself is in the east-west plane, so we can say that's east and that's west. Okay, so we've done part A, we've drawn our diagram. Part B says now show the direction of the vector representing the angular velocity omega on your diagram. So there's a couple of ways you can do this. You can use the right hand screw rule, which says that if you wrap your fingers around in the direction of the velocity, then your thumb points in the direction of the angular velocity, which tells us that omega is down here. Alternatively, you can use the right hand rule along with V is equal to omega cross R. And if we consider, say, a point here on the disk, let's change colors, let's consider this point on the disk, then my R vector is going from the center of the disk to this point. V is tangential at this point, so along there, so that's V. So using the right hand rule with these vectors and this cross product, you also get that omega is down the page. Okay, now part C now asks us find the angular velocity of Discworld. So now we just need to find omega, which is equal to how many radians it goes through in how much time. And we're told that the period is 72 hours. So that tells us that it goes through 2 pi radians in 72 hours. So 72 times 60 times 60 seconds. And solving that one on the calculator, we end up with 2.424 times 10 to the minus 5. But because the 72 hours is just to 2 significant figures, we should give this as 2.4 times 10 to the minus 5 to 2 significant figures. But it's good to have this because we'll probably need to use this for working in a little bit. Question D then says, what is the angular acceleration of the Discworld? Well, the rate of the rotation isn't changing, so the angular acceleration is equal to 0, and that's radians per second. Sorry, I forgot to write the units here. This was radians per second. And then E says, find the centripetal radial acceleration of a person standing right on the outer edge of the Discworld. So it's somebody standing here, say, and we know that the centripetal acceleration is equal to v squared on r, or we can write this same formula as omega squared r, which is easier because we've got omega squared already. So then we can substitute in 2.424 times 10 to the minus 5 squared times the radius, and we were told that the disk is 15,000 kilometers wide, so the radius from there to there is 7,500 kilometers. So that's times 7,500 kilometers, so times it by 1,000 to get it into meters. And solving for that one on the calculator, we get 4.4 times 10 to the minus 3 meters per second, and it's centripetal acceleration, so it's towards the center of the disk. And then F. Now we're going to consider the Earth, and we're asked to calculate the moment of inertia of the Earth. And so the Earth is a sphere, and on the formula sheet we're told that the moment of inertia for a sphere is equal to 2/5 mr squared. And then on the data sheet we're given the mass of the Earth. The mass of the Earth is 5.972 times 10 to the 24 kilograms. And the radius of the Earth is 6.371 times 10 to the 6 meters. So we square that, and that is equal to 9.696 times 10 to the 37, and the units are kilograms meters squared, and we've given it to 4 significant figures as we have the radius and mass of the Earth to 4 significant figures. Okay, so question 4, part A. So in this question we've got a PV plot. Let's just quickly sketch it over here. We've got points A, B, C and D. In the exam you could sketch all over the diagram that's in your problem booklet, because you hand in the problem booklet at the end of the exam. And part 1 of the question says, what's the work around the cycle? Okay, so I'd recommend writing on this diagram what we know. We know that going from D to A, the work done is equal to 0. We should put P and V. And going from B to C, the work done is equal to 0, because when the volume doesn't change, no work is done. So we're only going to need to calculate the work done going from A to B and going from C to D. So the work done going from A to B is equal to minus the integral of P dot dV. The pressure is constant, and it is equal to 3.00 times 10 to the 5 pascals. And then dV is the change in volume. So we've got the final volume, which is the volume at B, which is equal to 2.00 times 10 to the minus 3 minus the initial volume, the volume at A, which is equal to 6.00 times 10 to the minus 3. So solving this, we end up with 1,200 joules. We would expect it to be a positive answer because the gas is being compressed, and when gases are compressed we do work on the gas. Okay, now the work done from C to D is equal to minus P dot dV, and the pressure at point C and D is 6.00 times 10 to the 5, and then we do times the change in volume. So the final volume is equal to 6.00 times 10 to the minus 3, and the initial volume is 2.00 times 10 to the minus 3. So solving this one, we end up with minus 2,400 joules, and so the work done around the cycle is equal to the 1,200, and then we've got the 2 zeros minus the 2,400 joules, so that's equal to minus 1,200 joules is done on the gas around the cycle. Part 2 then asks us to calculate the temperatures at each point A, B, C and D, which is a bit tedious, so we can just use the ideal gas law for this. So the temperature at A is equal to the pressure at A, volume at A over NR. these are all values that we have. The pressure at A is 3.00 times 10 to the 5 pascals. The volume at A is 6.00 times 10 to the minus 3 meters cubed. N is 1 mole and R is 8.314. Solving this, we have 216.5 kelvins, so this is equal to 217 kelvins to 3 significant figures. And then the temperature at B is equal to the pressure at B, volume at B over NR. Now we could just substitute these numbers in, but to solve ourselves some time, I'm just going to relate it to A. So the pressure at B is the same as the pressure at A. The volume at B is a third the volume at A, just looking at the values given over NR. So the total is just going to be a third of what it was for A. So we can just divide this temperature by 3. And when we do that, we get 72.2 kelvins to 3 significant figures. The temperature at C is equal to PCVC over NR. Okay, so again, we'll relate that to what we had at A. The pressure at C is double the pressure at A, and the volume at C is the same as B, which is a third the volume at A. So that's N over NR. So this is 2/3 of the temperature at A, or double the temperature at B. So 2/3 TA, which is equal to 144 kelvins to 3 significant figures. And then the temperature at D is equal to PdVd over NR. The pressure at D is double the pressure at A. The volume at D is the same as the volume at A over NR. So this is equal to 2 TA, and so double this is equal to 433 kelvins. Okay, part 3 then asks us to find the heat transferred to the gas for processes B to C and C to D. Okay, so Q from B to C. Looking at going from B to C, this is a constant volume process, so we're going to have NCV delta T, and so that'll be 1.00. Now, CV is equal to a half F, so that's going to be a half, and then we're told it's a monotonic gas. So for monotonic gases, F is equal to 3, so it's a half times 3 times the final temperature, so TC, which is 144, minus the initial temperature, which is 72.2. And solving this, we end up with, sorry, I left off the R. CV is equal to a half FR, so times 8.314. And so solving this, we end up with 895 joules, and that's to 3 significant figures. And then we're also asked to find the heat transferred from C to D. Going from C to D, that's a constant pressure process, so it's NCP delta T. So that's 1. Now CP, looking at that, it's a half times 3 times R plus R. So it's a half times 5 times R, which is 8.314, times the change in temperature. So that's the temperature at D, which is 433, minus the temperature at C, which is equal to 144. So solving that one, we end up with 6,007 joules, and so that's 6,010 joules to 3 significant figures. And then part 4 says this is known as a heat engine. Its efficiency is the work out divided by the energy in, and only consider parts B to C to D. For Q as above, what's the efficiency? So the efficiency is equal to the work out over the energy in. So the work out I mean, it's not really clear from the question if we need to do the work out just from B to C to D or for the whole cycle. I'll do the whole cycle, but you could have done either of them. So the work out is equal to 1,200 because that's the work done on the gas was negative, so the work done by the gas is positive, which is the work out. And the energy in, this comes in as heat. So it comes in, we can add these two together, 895 plus 6,010. And solving that, we end up with 0.174. But it asks us to give it as a percentage, so that is equal to 17.4%. If we did just the work done from C to D, we'd end up with double this. Okay, question for part B. In this one, we've got a cup of coffee and we're told that the mass of the coffee is equal to 300 grams, so that's 0.30 kilograms. And the initial temperature of the coffee is 25 degrees C, and it's in a steel cup with a mass of 0.050 kilograms. And that also has an initial temperature of 25 degrees C because it's at thermal equilibrium with the coffee. And we put a sphere into it of steel, and the mass of the sphere is 0.10 kilograms. And the initial temperature of that sphere, so let's call that TS, is equal to 1,400 degrees C. And we're asked what's the final temperature after they've all reached thermal equilibrium. So the total heat transfer in this case is 0. Anything lost by the sphere is gained by the coffee and the cup. So we can write that the mass of the coffee times the latent heat capacity of the coffee, which we're told to model as water, times the change in temperature, so that's the final temperature minus the initial temperature. So this gives us the heat gained by the coffee plus the heat gained by the cup, which is the mass of the cup. It's made from steel, so the specific heat of steel times the final temperature minus the initial temperature, which is the same as for the coffee, plus the sphere. So we've got the mass of the sphere times the heat capacity of steel, because that's what the sphere is made out of, times the final temperature minus the initial temperature, which we're calling TS. It starts at a hot temperature, whereas the others start at the cold. And so what we're trying to do is find TF, which is common through all these terms. So we can rearrange this to give TF times the mass of the coffee, specific heat of water, plus the mass of the cup, specific heat of the cup, plus the mass of the sphere times the specific heat of the sphere, is equal to the mass of the coffee times the specific heat of water times the initial temperature, plus the mass of the cup, specific heat of the cup times the initial temperature, plus the mass of the sphere, specific heat of the sphere times the initial temperature of the sphere. Okay, and sorry about that line. Now rearranging it to work out TF, we just need to divide this by this. We've got the mass of the coffee times the specific heat of water times the initial temperature plus the mass of the cup times the specific heat of steel times the initial temperature plus the mass of the sphere times the specific heat of steel times that initial temperature divided by the mass of the coffee, specific heat, plus the mass of the cup times the specific heat plus the mass of the steel times the specific heat. And now we can substitute in, so we've got 0.30 times 4186 plus, times 25 plus the mass of the cup, which was the 0.050, times the specific heat of steel, which we're told is 490, times the initial temperature, which is 25, plus the 0.10 times the 490 times the initial temperature here was the 1,400, divided by 0.300 times 4186 plus 0.050 times 490 plus 0.100 times 490 and then we solve that on the calculator and we get 75.7 degrees C, which is equal to 76 degrees C to two significant figures. So it's fine to give the answer in degrees Celsius. Alternatively, you could have converted everything to kelvins, in which case if you substitute in for kelvins, you'll end up with 350 kelvins to two significant figures. Okay, so this is question for part C. And in this question, we're told that a third of the expected sea level rise is due to the temperature change, and if the initial volume of the ocean, so let's call that V0, is equal to 1.3 times 10 to the 21 meters cubed, in part 1 we're asked for a temperature rise of 5 kelvins, by what percentage will the volume increase due to the thermal expansion alone. So we know that the change in volume is equal to beta times the initial volume times the change in temperature. So this is equal to beta, which is 0.0002 per Kelvin, times the initial volume times the change in temperature, which is 5 kelvins. Solving this, we end up with 0.001 V0. And so as a percentage, if we times that by this 0.001 by 100, we get a 0.1% increase. Okay, and then, because what we're trying to calculate is just how much the volume changes compared to the initial volume, which is why we've left that V0 there and not substituted in for it. And then in the second part, we're told that the mean depth is 3.7 kilometers. Estimate the sea level rise caused by the volume increase. Okay, so we assume that the surface area remains constant. So this part here is constant, and any change in volume is due to a change in height. So we're going to end up with a 0.1% change in height. Okay, so the sea level rise will be equal to 3.7 kilometers times 0.001, and so that is equal to 3.7 divided by 1,000, or 3.7 meters. So we should probably only give it to one significant figure, as we only have beta to one significant figure. So we can say it's a 4 meter sea level. I put sea level rise. Okay, this is question 5. And we're going to do part A here. So in this one, we've got a oscillating mass on a spring. So we've got a spring here and a mass, and it oscillates away from its equilibrium position. And part 1, we're asked to sketch a displacement time graph for the mass, including as many details as you can. Okay, so because it's just a mass on a spring, it's going to undergo simple harmonic motion. So we can draw our displacement time graph here. So this is displacement from equilibrium. Now it starts at 0.10 meters, and so it's going to go back down to minus 0.10 meters, and we're told that at t equals 0 it's at this displacement. So it's going to start up here and then move sinusoidally up and down like this. So that's part 1. Part 2 then says write down an equation that describes how the displacement of the mass changes with time, including any necessary variables. Okay, so it's undergoing simple harmonic motion, so it's going to obey the equation x is equal to a cos omega t. Now, because this is a mass on the spring and we're given A, so we can substitute in for A, 0.10 is the amplitude, cos, now omega is the square root of K on M for a spring. K is the spring constant and M is the mass on the spring. So this gives us the equation for the simple harmonic motion there. And then part 3 says, show all your workings, state any assumptions, derive an expression for omega, the angular frequency of the mass, in terms of the variables given in the question. Okay, so we need to derive it. So we'll start with this expression here. So we've got dx dt is equal to a omega sine omega t, and we need a negative sign out there because when we take the derivative of cos omega t, we get minus omega sine omega t. And then d squared x dt squared is equal to minus a omega squared cos omega t, which we can write as minus omega squared x. Okay, now we're trying to derive the omega. So we know that F is equal to ma, which is equal to minus kx, because the only force acting on the spring is the Hooke's law force given by minus kx. And we've now got an expression for the acceleration here that we can substitute in. So this tells us that minus omega squared x times, that's for a, times m is equal to minus kx. So these x's will cancel out, the negatives will cancel out, and we end up with omega is equal to the square root of k on m. So that's derived that there. Maybe we should say Hooke's law. And this one here is Newton's second law. Just so that we've made it really clear that we know what we were talking about. Question 4, if the mass were replaced with a new mass, and the new mass, capital M, is equal to 4 little m, and displaced to the same initial displacement, what would be the expression for the angular frequency? Okay, so we've just got, in this case, omega is equal to the square root of k, and instead of 1m here, we've got 4m, so it's equal to a half k on m. That's a little m, a lowercase m. Okay, and then 5 says, draw a graph showing the relationship between the kinetic energy, potential energy, and total energy of the mass as a function of time. Where possible, write expressions for these on the axes, make any relationships clear, and show these for the cases with both the little m and the capital M. Okay, so let's draw it here. So this will be the energy, this will be the time. Okay, let's start with the case for little m, and we'll use different colors. Let's use blue for potential energy. So initially, all the energy is as potential energy when it's pulled far from its equilibrium position and it doesn't have any velocity. And then this energy gets converted into kinetic energy. So here's the potential energy. Somewhat wonky sine squared graph like that. Now the total energy, let's call that E, remains constant with time because there's no friction or anything, we're not losing energy. So the total energy remains constant. And then let's do green, this can be the kinetic energy. Initially it is at rest, and so initially it has no kinetic energy. So the kinetic energy is going to look like this. Okay, now what we need to do, we've done that for m, now we need to do it for the case for m. And for 4m, with a half k a squared, it's got the same amplitude, so it's got the same total energy. So we can say total energy is the same. But what's going to be different is that the angular frequency here is half the original angular frequency, so the period is doubled. So let's take dark blue to be U for 4M, which is equal to capital M. And so if the period's doubled, that means that when it went down and back up, and then down and back up, that's just going to go down and back up for this heavier case. So we can draw it a bit like that. And then we can, let's try and find is there a dark green colour? Here's a dark green for, that looks very similar. Is that better? For naps still. How about this colour for K? And again, it's got, the period is twice the period it was before, so it'll look like that. So the period's doubled. So it's good that we've written that for the marker so they can hopefully make out what's going on our slightly messy graph there. Okay, and then the final part says, under ideal conditions, would the mass ever stop? Well, no, under ideal conditions, it would not. If we wanted it to stop, then we'd need to introduce friction, which would be a damping force, and this would cause it to come to a stop. So no, we would need to make it stop. So then it would do work against the friction, which would lose the energy, and so our total energy would decrease with time. Okay, so this is question 5, and this is part B. And in this part, we've got a bell on a turntable, which is rotating this way about some axis, and there's an observer over here listening to the bell. And in the first part, we're asked to write an expression for the maximum frequency, F, that the person detects from the bell. Okay, so F max, this is going to be a Doppler shift question, and it's going to be F, now velocity of the air, we're told to use VA for the velocity of the air. The observer is stationary and so is never moving. And then we've got the velocity of the air, and we've got minus or plus the velocity of the source here. Now to get the maximum value, we're going to need to have minus the velocity of the source here. But in the question, we're told that the bell is at radius r, and this turntable is rotating with an angular frequency omega t, and we know that v is equal to omega r. So we can work out what the velocity of the source is. So this will be F VA over VA minus omega subscript t r. And so that will be the maximum frequency. Now part 2 says, sketch a diagram that clearly shows where the bell is relative to the person and how it's moving when the maximum frequency is heard. Okay, so the maximum frequency, we have a negative sign here. We have a negative sign when it's moving towards the observer. So we want our source, our bell, moving towards the observer with the maximum possible frequency. So that will be when it's here on the edge and it's traveling with speed v. So that is our diagram showing that there. And then part 3 says, write an expression for the minimum frequency that the person detects from the bell. Okay, so the observer is still not moving, so we have nothing up the top here, and we'll get a minimum when we have a plus omega t r down here. So that solved part B. Okay, question 5, part C. So here we've got a standing wave set up on the string. The length of the string is 1.25 meters. The mass hanging from it is 250 grams or 0.250 kilograms. And the frequency generator is set to 77 hertz. And looking at the string, we've got 3 loops. So we can say that we've got 3 half wavelengths. So 3 over 2 lambda is equal to 1.25 meters, which tells us that lambda is equal to 0.83333 meters. And the first part asks us to calculate the mass per unit length. So we know that V is equal to the square root of T on mu, and it's also equal to F lambda. So rearranging this, we end up with mu is equal to T over F squared lambda squared, where T is the tension, so that's mg. So it's 0.250 times 9.80 over F squared, which is 77 squared, times 0.8333 squared. And so solving this one, we end up with 5.95 times 10 to the minus 4 kilograms per meter. And so that is equal to 6.0 times 10 to the minus 4 kilograms per meter. Okay, now part 2 then says what frequency will the frequency generator need to be set to in order to observe the next harmonic. Okay, there's a number of ways that we could do this. We could work out the wavelength for the next harmonic. Another way to do it is to realize that, well, at the moment it's the third harmonic, and that's 77 hertz. And that is equal to 3 times the first harmonic. The next harmonic will be the fourth harmonic, and that will be 4 times F1. So that is equal to 4 times F3 on 3, which is 4 times 77 on 3. And then solving that on the calculator, we get 103 hertz, but 77 is only to 2 significant figures. So this is equal to 100 hertz, and that's to 2 significant figures. And that's the end of the exam paper.